Today, I'm pretty excited to bring you a tutorial on Kubernetes. We're going to be installing Kubernetes into our Proxmox cluster, which is basically installing it on bare metal. As a junior DevOps engineer, this is how I learned Kubernetes, by installing it and breaking it on a daily basis, learning from my mistakes. I highly encourage you to do the same. As a DevOps engineer, or anyone striving to become one, mastering Kubernetes has become more and more important in the global market. 92% of large and medium sized organizations are actually using Kubernetes for their containerized applications. But this is not only large and medium sized organizations, but also 78% of small organizations are using Kubernetes as well. In this video, I want to talk about how we're doing the architecture layout, K3s versus K8s, the subnetting and resource requirements for Kubernetes, and of course, deploying a multi-master cluster with Kubespray. So now, I know this topic can be intimidating and has been done a few times. However, I think there is a clear market gap with how much people actually know about Kubernetes being deployed, as they likely deploy K3s instead. So if you want to skip the why and the why not and instead just get to how we're deploying Kubernetes, go ahead and hit those chapters down below and you can skip to whatever part you want. So now, let's get into it and dive into why we should learn Kubernetes. Let's think about the banking industry here. Transactions are going to be at their highest during the middle of the day and the lowest during the middle of the night. You will also have intermittent peaks around the holidays. You will have scaling issues that normal servers just cannot maintain. So what do? Well, Kubernetes helps you solve this by automating that scaling factor, right? It can look at how many transactions you have in queue, and then based on that, it can scale up or scale down the amount of pods you have deployed. The banking industry is also mandated to have a specific amount of uptime, usually by governments or SLAs with larger clients. Kubernetes also solves this by allowing it to scale up and scale down if a node goes offline. Often you hear about deploying Kubernetes as K3s. However, these are not the same. While they offer a compatible interface, the deployment methodology and other information under the hood is different. When it comes to Kubernetes, we have more enterprise features. This includes built-in support for complex networking layouts, storage, and cluster configurations. And because of this, we will have a high degree of flexibility and extensibility and customization. However, some of the trade-offs are that we will have a steeper learning curve and more components to manage, but we will have a larger community and more third-party integrations here. On the other hand, if we look at K3s, we will have limited features. Because this is lighter weight and has limited features, it will also be good for edge deployments or IoT devices. However, this is not good for learning, as we want to make sure that we can experience all the features that Kubernetes has to offer. So I'm going to highlight a few options here to show you why you should choose Kubernetes versus K3s. To be clear here, both are solid projects and both have their trade-offs. However, if you don't have exposure or are trying to learn Kubernetes administration, or you need to deploy complex applications, it is my thoughts and many others that you should run Kubernetes. Now that we know we're going to deploy Kubernetes and not K3s, why are we choosing Kubespray? Well, Kubespray is actually one of the recommended methods of installing Kubernetes and actually leverages kubeadm to install Kubernetes as well. So it's really listed here twice in the Kubernetes official documentation. Now, Kubespray is a composition of Ansible playbooks, inventory, and provisioning tools, but it's also a domain of knowledge for Kubernetes clusters and configuration management tasks. It offers a way to install, upgrade, add, and remove nodes, and even reset your nodes if you want to test out other implementations of CNIs or want more practice with other configurations. Kubespray offers the ability to customize many aspects of the deployment. This includes your DNS configuration, your choice of control plane, whether it's binary, native, or containerized, component versions, Calico route reflectors, and even component runtime options such as Docker or Containerd. Kubespray customizations can also be made via a variable file. However, if you're getting started with Kubernetes, consider using the Kubespray defaults to deploy your cluster and explore Kubernetes at a base deployment. Before we begin, let's talk about how we're going to lay out our Kubernetes environment. For Kubernetes, there are a few requirements that we have to have in order to run it. One is that our machines have to be run Debian or an RPM-compatible Linux OS. For us, this is going to be Ubuntu 22.04. The next one is that we have to have at least 2 gigs of RAM or more per machine, as any less leaves little room for your apps to run. So for us, we're going to put 4 gigs on the control plane and 16 gigabytes for our workers. Another requirement is that we have at least 2 CPUs per machine to use as your control plane node. For us, we're going to be assigning 4 cores to each machine in our cluster, and we'll address this later as needed. Additionally, we'll need to have full network connectivity amongst all our machines in the cluster. You can either use public or private, but for us, we're going to be using a private network. So let's talk about how we're going to lay out our Kubernetes cluster inside of our Proxmox cluster. So for our cluster, we're actually going to be using the first 3 nodes in our Proxmox cluster. We are going to first spin up 3 control plane nodes, each on one of our Proxmox servers. These control plane nodes will consist of 4 cores and 4 gigabytes of RAM. Next, we're going to spin up 3 more worker nodes, which will consist of 4 cores and 16 gigabytes of RAM each. We will lay out these nodes in a /24 network, and our control plane nodes will be allocated to a /27 beginning at .32. As for our worker nodes, we will allocate these also in a /27, but we will start at 128. This will allow us to assign IPs in a sequential order and allow for expansion in the future if needed. So let's take a look at the GitHub repo for this because I want to highlight an issue I ran into when spinning this up in the past. Now, as you can see on their GitHub, if you click here in the top right, you'll be able to see a main or master branch for this project. Now, when I previously deployed this in the past, this was not stable. So what you actually have to do is go to a release on the side here and select which release you want to deploy of Kubespray. And I highly recommend doing this as it will make sure that the release is stable and you won't run into any issues where it potentially just breaks in the middle of the deployment. Inside of the releases package, we can see that the latest tag that we want to have is 223, right? So we know what tag we want to pull down when we're actually cloning this to our desktop. Now, let's run Kubespray and deploy Kubernetes to our environment. There are 2 methodologies to accomplish this. During the video, I'm going to use a virtual environment recommendation. However, at the end of the video, I'm going to show you how to leverage their Docker container as it is my preferred methodology. Prior to running the playbook, we need to generate our inventory and then configure our variables we want to change. To generate our inventory, we need to first clone the Kubespray repository and then check out the release tag. So let's run a git clone and then paste in the link from the repository. After switching into the repository folder, we will need to run a git checkout tags /v2.23.0. This will put us on a specific release tag that we want to have for our runtime environment. Now that we are on the release tag, we want to run a command found in the documentation for installing the requirements text. So the first thing we want to do is to set up a virtual environment using Python, and we're going to name it Kubespray-venv. The next thing we want to do is to activate our virtual environment and then install our requirements text using pip3. So now that we have our environment set up, we're going to copy over a sample inventory into a new inventory folder. This will initialize all the defaults for our Kubespray playbook that we're going to deploy to our nodes. Next, we're going to declare an array of variables called IPs. This will contain all of your cluster IPs that we want to have configured. So we're going to type declare-a, and then our IPs are going to be equal to our node IPs, making sure to leave a space in between each IP. Finally, we want to run an inventory Python script found in the repository, which outputs the host YAML in our inventory location and takes in our declared IP variable. And as you can see from the output, we have all our nodes added to an inventory file. Next, inside of VS Code, we can see that we have our new inventory folder generated with our host YAML file. Inside of our inventory file, we need to make sure we modify the node names. Otherwise, it will rename your nodes, and this could lead to a problem with DNS resolution. Also, we will want to make sure we modify our control plane group to have the 3 nodes to match what we discussed earlier. With that, we have our inventory up to date with what we discussed earlier. Next, we will want to define a variable file that we're going to pass into our playbook command. So let's create a cluster-variable.yaml file to hold all of our variables. The first variable we will want to modify is our kube version. When deploying anything, it is always good to try and pin it to a specific version. That way you know there will be no unexpected change to your environment. To do this, we will need to define a kube_version entry. In this case, we're going to pin it to a release version of v1.27.5, since this is a new cluster. Next, we will want to define a common Kubernetes tool of Helm. Adding Helm _enabled True, we'll configure our cluster to have Helm installed when we go to deploy applications later. The third thing we want to change is our kube proxy mode. For this, we will be setting kube underscore proxy underscore mode equal to IP tables. By default, Kubespray will deploy a cluster with IPVS, which is not installed by default on our nodes. IPVS is not required for our cluster as it is a small deployment. However, I will leave articles in the description for comparing IPVS and IP tables. This way you can choose the proxy mode you prefer. Finally, I'm going to insert a comment that would normally enable MetalLB. However, when deploying this previously, it seems like Kubespray is not properly installing MetalLB. Thus, I'm going to leave this commented out in our variables file in case we want to revisit this in the future. Because this will not get installed at this point, I will touch on what MetalLB is and why it is required for our Homelab install when we go to install this later. And that's all the variables we will need to configure. Of course, there are a lot more, but I will leave a link below to their documentation for the others. Following that, we can bootstrap our cluster. Back in our terminal, let's kick off the Ansible Playbook command, passing in the additional arguments we will need to define for our deployment. We are going to pass in our inventory file and our variables that we've defined earlier. Yes, the @ is required here. We will also need to pass in a become and a become user argument to grant elevation rights to the Ansible playbook so it can use sudo when required. Additionally, for my deployment, this will be running under my Ansible user, so I'm going to pass in that as well. If you are deploying this in your home lab, you will be using your SSH user that you connect the machine with. Finally, at the end, we're going to put in our cluster YAML file, which is the playbook for the install. Hitting enter here, we will see a flurry of output. This should take about 18 to 20 minutes for our deployment, so I'll see you in a few minutes. Welcome back, and as you can see, we've finished running our playbook, but now we want to scroll up and confirm there are no failures from our run. And as you can see, there are none, so we are good to go. Following this, we are going to SSH into our control plane server. For me, I am going to SSH with my Ansible user by running SSH Ansible at k8s-cp-01.home.local. Inside the server, we want to open our kubeconfig file, which is located at etc Kubernetes. So first we need to elevate to our root user and then run cat etc kubernetes admin.conf. Now let's copy this file and go back to our host machine. On our host machine, we will first want to create a directory in our home directory of .kube. Then we will use vi to create a file called config in that folder. Inside of vi, we will want to paste in our config, making sure to modify the server address to point to one of our IPs for our control plane. Saving this file, we will be able to run the kubectl get nodes command to validate all of our nodes are in a ready state and waiting for a workload. With our Kubernetes cluster up and running, I want to test and make sure that we can deploy an application and that it comes up without any issue. In order to do this, we're going to leverage a service called Helm, which is a package manager for Kubernetes. Using Helm, we're able to find different containers and different applications that can be easily deployed so that we can test our application. For our test, we're going to be using Nginx. This is not the Nginx ingress controller, but it is just an application that can be used to expose a web front end so we can test that our applications are being deployed correctly. So in order to do this, we're going to run a Helm install, passing in a myRelease tag, which will be the name of your release, and then we're going to use the OCI pointer pointing to their registry and their repository that they've defined inside of this chart. And then we're going to point to the Nginx chart inside of the repository. So now let's switch over to our terminal and run this command. As you can see, we've modified the OCI command pointing to registry.docker.io/bitnami charts/nginx. This will allow us to pull a latest release for our Helm chart, and then we can go ahead and install this in our Kubernetes cluster. So now let's check on the status of our pods prior to checking to see if we can reach it. So we're going to run kubectl get pods, and we can see that our Nginx pod is up and running. So now we can also check to see how we can connect to this by looking at our kubectl service with our default namespace. However, the biggest issue we can see here is we do not have an external IP. Instead, this is stuck in a pending state. This is where MetalLB will come into play. So now that we know our problem is with our networking for our service, let's take a look at how Kubernetes does our IP address and assignment for our service that we want to expose. Inside of Kubernetes, each pod will get its own IP address that will allow internal pod communication between replicas and things of that nature. However, for internal services inside of the Kubernetes cluster, you will need a service that is exposing a different IP of type cluster IP. This will create a different IP that your front end service can use to connect to the MySQL database on the back end. You will not be able to connect to it directly. However, when we give this same IP address to our end users to try and connect to the MySQL service, they will get an error saying connection failed because that IP is not within the scope of the routing tables that they have outside of the Kubernetes cluster. We will instead need to switch this over to a load balance service, and that way we will get an external IP assigned to it, and then our users will be able to connect to this service successfully. However, when it comes to our cluster, we are getting an external IP that is in a state of pending. So we do not know what IP address to give our users in order to establish a connection. So now, why are we in a pending state? Well, by default, Kubernetes does not offer an implementation of network load balancers for bare metal clusters. The implementation of network load balancers that Kubernetes does ship with are all glue code that is associated to various IaaS platforms like GCP, AWS, and Azure. And if you're not running on a supported IaaS platform, load balancers will remain in a pending state indefinitely. Bare metal cluster operators are left with two lesser tools to bring traffic into their cluster: node port and external IPs. Both of these options have significant downsides for production use, which makes bare metal clusters second-class citizens in the ecosystem. However, we're going to work around this by installing MetalLB. And MetalLB aims to reduce this imbalance by offering network load balancer implementation that integrates with standard network equipment. So let's take a look at how we can actually install and what this looks like for MetalLB system. So when we install MetalLB, we're going to deploy a daemon set that is in the MetalLB system. This daemon set will reach out to our NIC and establish a connection and pull information from that NIC. From there, we will assign and create two different types of kinds for the MetalLB system. One is an address pool that will define the range of IPs that we want to expose from Kubernetes. The next one is a kind of L2 advertisement. This will allow you to expose specific IP pools on specific nodes. This can be useful for when there are scenarios where only a specific subset of nodes are exposed to a given network. This will allow you to limit those nodes as potential entry points for service IPs. So now, instead of our load balancer staying in a pending state, we will instead assign that IP, advertise it out, pointing it back to our MAC address for our NIC. So now that we know how MetalLB works, there's one more thing I want to touch on before we actually install this. If you opted to use IPVS in your installation, you will have to enable strict ARP. This is mentioned in the installation documentation, and I'll leave a link to this below. So now if we scroll down, we'll be able to see that we find the installation by manifest. This will actually install MetalLB and the system namespace into our Kubernetes cluster. So now we're going to copy this down and run this against our Kubernetes cluster. So now that we have our manifest installed, we are going to create a new folder inside of our inventory to define how we are installing MetalLB and the different kinds we will be creating. So as mentioned previously, we need to create an IP address pool, and we're going to do this by actually creating a IP address pool.yaml file, and we're going to actually insert our IP address pool definition. For me, I'm going to be exposing 172.16.43.1 to 172.16.43.128. And you can actually define different ranges if you want to do different subnets or different ranges of IPs to divide up your subnet further. Next, we're going to be creating another file for the L2 advertisement YAML. Inside of here, we're going to paste in a L2 advertisement with a name of default advertisement. This is because we're not limiting what IP address pool we're going to be picking from in order to define out our advertisement IPs. Next, we're going to jump back into our terminal and actually apply our definitions that we set up. So we're going to run kubectl apply -f and pass in our path to our MetalLB definitions. Once they're created, we can run our kubectl get service command, and we can see that we now have an external IP defined. Copying this external IP, We can see that we're able to access our Nginx ingress by going to that IP because it is exposed on port 80. So now that we have our Kubernetes client set up and using the virtual environment, let's talk about how we can instead leverage their Docker container. This will just be a repeat and a summation of how I can use the Docker container to do the exact same thing, except we will be using the tag from the Docker container instead of having to check out a specific tag in Git. I will put this into the Pragmatic Engineering YouTube organization on GitHub and also leave a link to this down in the description below so you can understand exactly what's happening here. So inside of our run.sh file, we have a image tag declared at the top, and we're going to be doing a Docker pull of the Kubespray container with that image tag. We are then going to run the Docker container, mounting our inventory into a root inventory file. We're going to mount our scripts into the root inventory file, and we're also going to mount our IDRSA file into the container as well so we can use it for Ansible. We're then going to run the bash command so we can get into the container and run our Ansible playbooks from there. So let's run this script now. So as you can see, we are inside of the container in the Kubespray directory. So inside of our container, we should be able to list out our scripts and make sure it's mounted correctly. So as you can see, we got our cluster script and our generate inventory script. If we look at our generate inventory script, we can see that we're naming out the Proxmox cluster that we're deploying. In our case, for this example, we're going to be using Proxmox1 instead of Proxmox01. From there, we're going to be copying the same sample directory and placing it into our inventory, declaring our IPs, and then putting our host YAML into that same inventory file. So let's go ahead and run this. And as you can see, our Proxmox folder got created for our inventory. For brevity's sake, I'm going to copy our Proxmox host file that we set up earlier in our virtual env into our host file here. From there, I'm also going to copy over our cluster variables that we set up earlier. Now, inside of our container, we can actually run this cluster sh script. This will check that we're passing in an inventory and our directory actually exists, that we have a host file being defined, and that we have our cluster variables being defined. You'll see at the very bottom that we were able to kick off the Ansible Playbook command, passing in all of the variables that we needed earlier. Remember, if you're running this locally, you may need to change your Ansible user. So now, in order to kick off this script, all we have to do is run scripts cluster and provide it the inventory that we want to run it against. So we're going to run proxmox1. Now, if we hit enter, this will start to run our playbook. The reason I like this methodology better is because it allows you to maintain a whole Git repository without merging in their code. This will keep your inventory along with any other clusters that you set up separate and organized. You will also be able to expand your scripts folder into actually running other scripts more dynamically or other playbooks more dynamically to upgrade or add nodes as we expand our cluster in the future. And that's it. Hopefully you have your Kubernetes cluster up and running. If there's any issues you ran into, please reach out to me in the comments below. If you enjoyed this video, please like and share as it helps our content reach more people. Now before we go, there's a couple things I want to say. One, if you made it to the end of the video, please like, share, and subscribe as it helps me greatly. Secondly, thank you all for 100 subscribers as it means a lot to me. My goal for the end of the year was only to reach 100 subscribers, however we blasted past that right in the middle of October. This really helps to motivate me to produce more content and make our content even better in the future. If you'd like to see something specific on this channel, drop a comment below and I'll respond back to you to see if we can make that happen. Thanks again. This is James from Pragmatic Engineering.